All right. Happy Friday. That's right. And the last day of instruction. That's awesome. So let's tackle it, get through it, and we'll be done with going through all of Calc 2. You survived. Look at that. And then Monday, I'll be here at 7:20. I won't be lecturing, but if people are here, I'll go ahead and talk about what topics are going to be important for the final exam. I hope to have the final exam study guide out before Monday. That way, if you want to work on the final exam before or work on studying for the final exam over the weekend, you could totally do that. Yeah, so there we go. Today is the last day. All right. Recall last time we were just diving into 10.4, another fast section. These are all very fast sections because they all revolve around pretty much all of this unit of material revolves around arc length and surface area, right? So, but even surface area revolves around arc length. So let me actually, I'll summarize that when we get to the end of the section. How's that? Because we're going to have one more arc length formula. That way we can just write them all down all at once. What we had started with last time in this section was polar areas, quote unquote, under polar curves. And I say quote unquote, because technically it is not really under in a traditional sense. You have the pole, and it's the area from the edge of your graph here, the edge of the polar curve, to the pole. That's the area, actually. You're just taking slices, like a slice of pizza. You're taking little slices. That's how you're finding the area when you're doing polar areas. A little bit different. It fans out like that. But mechanically, it copies what you did in your trigonometry course. In your trig course, you found that the area of a sector was 1/2 r squared theta. Well, here, since we're just looking at each little subsector separately, we say the area of that little ith subsector is, well, 1/2 r squared theta, or r squared d theta, because it's a wiggle in theta. And the r is actually the polar equation of the edge. This edge right here is r, which is a function of theta. Just the distance you're throwing a rock in front of you or behind you depends on what angle you're facing. All right. I keep using that rock analogy and throwing things just because that's the habit that I have. Sorry about that. So we started going through and finding areas, quote unquote, under polar curves. And this required a little bit of a shaky footing for a lot of us as we go through and do this work, because a lot of people don't graph in polar coordinates enough to feel expert, like feel really comfortable with graphing in polars. And so I had made mention last class that I do expect you to know how to graph polar curves of these two forms pretty quickly. So some number plus or minus some number sine or cosine of theta, or r is equal to some number times sine or cosine of theta. These two right here are actually just circles of diameter, not radius, but diameter, a lead coefficient right there. So, and they're either y-axis heavy if you're dealing with a sine, and it'd be the positive y-axis if a is positive, or the negative y-axis if a is negative. Same thing for the cosine. Positive x-axis if a is positive, or the negative x-axis if a is negative. Those are kind of the easiest. And then you have these two right, this type right here, and this actually is 3 different kinds of polar curves. There are lemniscates, well, actually not lemniscates. There are lemnisons and lemnisons with inner loops. Lemnisons themselves, they have 2 subcategories. So you'll have cardioids, where here's the pole. That's a cardioid. I don't really care about that, you know the name. I'm just telling you that's what it is. This is a very typical where limicon, where that's the pole. And then we saw the other one last time where it goes through the pole and has an inner loop. Those are the three types of limicons that you would see with this these polar equations here. And I don't really care how you memorize those. You could watch my video on the review of polar curves and whatnot. And I talk about this stuff there. But eventually you just want to be really good with these specific ones right here. There are other ones that you will see, and we'll see it actually as our first example. You'll see other ones like this. R is equal to, let's say cosine of 3 theta, or sine, R is equal to sine of 6 theta. These are roses. This the 6 theta is a 12 petal rose, and the 3 theta is a 6 petal rose. So these are, or actually, I think the 3 theta is actually a 3 petal rose. But anyway, they are really hard to draw accurately by hand. And so if something like that occurs on a homework or on an exam, I would give you the curve. I would actually give you the graph of that specific polar, that because it's just a pain to spend, 5 or 10 minutes of precious time on an exam trying to graph your trig, especially rare trig like this. So be aware that if I have something like one of these two where you have multiple angle versions of your sines or cosines, that I would give you the graphs. So don't freak out too much about those. So again, the ones you really want to know are the ones I listed above. Although there's some special versions like this. R is equal to square root of theta. As theta grows, so does R. And so that you should be able to kind of guess at the graph, and that graph would be this like conch shell or whatever you want to call this. And so we started our entire process finding the area, quote unquote, under this polar curve. And then once we did that, we did limicon with an inner loop. And this is where I really kind of focused on the fact that if it's a positive sign, it'll be the positive y-axis heavy. You can see that it is. Most of the graph is in the positive y direction. And then I just plot the 4 critical points, and that just helps me figure out what kind of shape it actually is. Does it have an inner loop? Does it not have an inner loop? Does it just come back to the x-axis or the pole? So those are things that you have to worry about there. If you're asked to find an inner part, you have to find when you enter this inner loop and when you exit this inner loop. Or you can find the angle with which you enter the inner loop and maybe halfway through and just double that up to find out that area. And so I wrote all those in the notes here. And then we went to this idea, well, what if we don't want the full area underneath the curve, but what if we wanted the area underneath some outer radius, but excluding some inner radius? And that ended up being this formula right here, 1/2 r sub outer squared minus r sub inner squared. It's because you're taking an outer region, and we know the area underneath an outer region is this. And you're subtracting the area underneath the inner region, and we know the area under the inner region is just this. And so if you factor out the d thetas and the 1/2, you get r naught squared, or r outer squared minus r inner squared. And then we ended Wednesday's class by doing that. Find the area of the region that lies inside this first curve. And as I mentioned right at the beginning today, anytime that you see r is equal to some number times the cosine or some number times the sine and no other action going on, that is going to be a circle of diameter 15 in this case. And it's going to be positive x-axis heavy. So if you take a look at our blue curve there, that's the diameter 15 circle. And it's mostly on the positive x-axis. There was the pole right there. And then we wanted the area inside that, but it had to be exclusively outside of the other curve. The other curve is 7 plus the cosine of theta. That's not a circle. That's actually a limicon. And so I did the same trick as I did with the previous page, where I just plotted some very quick values. So if I color code it here, facing angle 0 and plotting 8 units out, you get there. Facing angle pi over 2 and plotting 7 units out, you get there. So you can see the path of travel. Facing an angle of pi and plotting 6 units out, you get there. And finally, facing an angle of 3 pi over 2, you plot a point 7 units out. And that gives you kind of a basic idea of which of the shapes it is. It's not a circle. It actually, if you really want to see what it truly looks like, it technically bows out a little bit more there and then comes back in and then bows back out and does that. So it has a little bit more of a hump to it. It's not that big of a deal, but it's just kind of an interesting little note that technically it has that look to it. But generally speaking, when graphing polars, I don't know very many people are that particular about how beautiful your polar curve has to be. And then we stopped there. I didn't really finish it out. So that's what we need to do here. We need to figure out how to compute that highlighted area. And we decided to just compute the area here, all these little spokes going out. Actually, it wouldn't be the spokes going out from there. It'd be the spokes going out from the origin. I should erase that. So we're going to find this area right here, and we're going to double it so that we get this area as well. And when we do that, we'll have these little spokes that were emanating from the origin, honestly. And these will be our little slices that we find the areas of. Not a big deal if you can't draw that perfectly, whatever. But that's why I said here, oh, it's doubled, because normally it's just 1/2 r squared theta, but because we're doubling it, it's 2 halves. And we're starting by facing the angle of 0. That's this way. That's theta equals 0. And we're going to stop when we face this angle right here. Whatever that angle is right there, that's where I want to stop. So we need to find out, where do these two curves meet? Where does the green curve and the blue curve meet? And by the way, just to let you know, this was our outer radius. 15 cosine of theta was our outer radius. That's that blue curve. And our inner radius was the green curve. This is r sub inner squared. Okay. So the only task we have, find that angle where they meet. Find out when they meet. So I will use blue, and I'll go off to the left-hand side here, and I'll say these two curves meet. I'll say when 15 cosine of theta is equal to 7 plus a cosine of theta. So all your trig skills get engaged at this point completely. Subtract cosine of theta from both sides. You get 14 of those cosine of theta equals 7. And then divide both sides by 14. You get the cosine of theta as 1/2. Now, there are an infinite number of solutions to this equation. However, I'm only really interested in the solutions between angle 0 and angle pi over 2. That's the only time that I really care about those two curves meeting. Do they meet at some angle between 0 and pi over 2? And the answer to that is totally, yeah, they do. The theta here has to be pi over 3 because cosine of pi over 3 is 1/2 from our special triangles. So I happen to know that's where they're going to meet. Pi over 3. And the rest of this is just computation. And as I mentioned earlier in the last session, that areas, like when you're working with polars, the mathematics is a little bit easier because, one, you're dealing with trig functions, and generally trig functions are slightly easier to work with when integrating. But also, you're dealing with squares of trig functions, and squares of trig functions are incredibly nice because, let's say I have a sine squared and then I have a cosine squared in the integrand. You can add them up; they become 1. So there's a lot of little cool tricks that you get here. Say this is equal to the integral from 0 to pi over 3. I already know that everything's in terms of theta. This is going to be 225 cosine squared of theta minus, and now I'm going to square all that out. That's 49 minus 14 cosine of theta. Let's see, minus cosine squared of theta d theta. And then I do some computations, right? So this is going to be the integral from 0 to pi over 3. Most of this I could skip. I know that one of my colleagues loves to just skip all the arithmetic in the background, but I just tend to finish it out. Every once in a while I'll skip it, but I like to finish these out. All right. With the risk that I'm going to make an arithmetic mistake, right? Okay, so just to remind you, there's a half angle identity to help us work with that cosine squared. So we'll have 1/2 of 1 plus cosine of the double angle. So 1/2 of 224 is 114. No, 112. As I said, my arithmetic. And then minus 14, the antiderivative of the cosine is the sine. And then minus 49. And this is the one that people hate because, 49 theta. Because you end up having pi's in your answer rather than just nice ratios. All right. So, and then from this point forward, it's just computing, right? 112. Theta, let's see, plus 1/2 sine of 2 theta. That's going to be evaluated from 0 to pi over 3. I always want to check in the chat to make sure you're not catching me on making mistakes here. Minus 14 sine of pi over 3 is root 3 over 2. Sine is 0, 0, so I don't even bother with that. Minus 49 times pi over 3. And then, again, 0. That's okay there. Distributing things through here. 112 pi over 3. Let's see, plus 1/2. Sine of 2 pi over 3 is still a root 3 over 2. Plugged in zeros, those are all zeros. Nice. Another thing that I kind of like by doing all this mechanical work in front of you guys is that it gives you time to think about what just happened or what we've been going through. So anyway, 51, 61, 63 pi over 3, which, by the way, 3 goes into that. What is it? 21 times. Yeah. So it's 21 pi. And then let's see, root 3 over 4 minus 28, so minus 27 root 3 over 4. Yep. There we go. That is the area outside of the green curve, but inside of the blue curve. Completely done. Not bad. You've got to times 112 in the second terms. Did I? I did. You're absolutely right. So this is not correct. 112. I'll let 2 go into that 112 then. That just makes the math actually slightly easier. 2 goes into 112, 55, 56 times. Let me just double check that. 56, yeah. And actually 2 goes into 56, 25, 28 times. 2 goes into 14, 7 times. There we go. Minus 21 root 3. How's that? Thank you very much, then. Okay. That's still a positive area. I was kind of worried that wasn't going to be positive, but that is positive. That's a positive area. All right. Right. Perfect. Thank you for catching me. And that is one style of problem. That's actually the most popular style. Something that's not super duper popular, but that does come up, and it's kind of annoying, to be honest with you, just because of the fact that you're dealing with these multi-petal roses, is what we'd call them, is finding the area that lies simultaneously inside both curves. Now, that word simultaneously, if you guys are not strong on the language skills here, that just means that you want to find the overlap. What do they have? Where is their intersection? Simultaneously means intersection. There we go. So for example, if you had something like, I don't know, some curve like that, that's a terrible curve. I'm just drawing something. And you had another curve that looked like this. Okay. Then the stuff that lies simultaneously within both curves is this stuff right here. It's within the black curve and the red curve. And so that would be the simultaneously occurring region. The stuff in here is only within the red curve, but not within the black curve. The stuff here is within the black curve, but not in the red curve, and so on and so forth. So that's what I mean by simultaneously. It's kind of a cool picture now that I'm looking at it. So if you want to, a quick primer on the multi-petal rows, I'm going to share my screen, my Desmo screen here. You can kind of do it yourself in a way, right? You know how to do that. I'm going to go to reverse contrast again. I don't know if people like the reverse contrast or not, actually. I have no clue. But what I'm going to do is look at the sign. The sign of 2 theta gives me a 4-petal rose. If I change that to the sign of 4 theta, it gives me an 8-petal rose. So it seems like whatever number is right here, you double it. Well, what's sine of 3 theta? And that's the annoyance to me. When it's an odd number, it's that number of petals. So an odd number will give me 3 petals, 5 petals, 7 petals, that type of thing. An even number will give me twice the number of petals. And then if I turn that off and turn on the cosine, even number of petals is again twice of number. So 4 petals, or 4 theta gives me 8 petals, and so on and so forth. And an odd number, again, sticks within the same odd number. So when it's odd, you have the same number of petals. When it's even, you have double. But luckily in this case, we are just dealing with this picture right here. I'm going to turn off the grid so you can actually see it nicely. We want to find what's common, what the common area between both of these curves. So I'm going to kind of chicken scratch that out on my laptop. Let me go ahead and go to my laptop. Again, if this was on a quiz, or not quiz, because we're done with quizzes. If this were on an exam, I would just give you the graph of it. Because generally speaking, there's too many things that can go wrong if I just say, find the intersection of these 2 multi-petal roses. A lot of students couldn't get to the calculus. They would be stuck kind of with their old school, very rarely used polar graphing skills. Now, I do want to say graphing polars is going to be incredibly important as you move into Calc 3. but not multi-petal roses. That's why I'm not that much of a stickler about them. So don't worry about that. All right. So since I'm sharing the screen now, I will try my best to showcase what this looks like. So we have a pole right here. There's the polar axis. And the sine, we'll deal with the sine's the harder one to do. We'll deal with the cosine. The cosine I'm going to do in red. By the way, this is actually how the cosine graphs out. It actually follows that path. If you think about it, when theta is 0, cosine of 0 is 1. So when I'm facing an angle of 0, I'm throwing a rock 1 unit out when I'm facing an angle of 0. So that's kind of why that it starts there. And then as you're turning through an angle theta, the rocks that you're throwing in front of you get closer and closer to your feet, because again, if you look at the cosine curve, that's exactly how the cosine curve normally goes. You throw a rock far away and it gets closer and closer to your feet until you drop it at your feet. So that's just a heads up. That's why I know that path of travel is like that. However, beyond there, it starts to get a little messy. It looks something like, I'll show you the real path of travel here. It looks something like this. So it continues this way. You can see why it would suck to have to do this by hand. Then it's a smooth curve. It's as if you're never lifting your pen when you're drawing it. Trying to be at least somewhat accurate and also go with the flow of the curve, but it's hard for me to do that. That one was easier. There we go. So that's a completed, it looks pretty bad actually, but that's the completed, that's the completed 4-petal rows. How do you graph those is the question that kind of came in the direct message part of the chat. Give me a moment while I take a sip. Well, I don't like to graph these at all, because you use a lot of symmetry. You use your knowledge that if it's an even number, it has twice that number of petals. Okay, same thing for the sine, by the way. It's twice that number of petals. So I happen to know there's going to be 4 petals for this. And generally speaking, I know how they're spaced as well. Each petal is 90 degrees off from the previous petal. That's if you have 4 of them. If you have only 2 of them, they're 180 degrees off from each other. If you have 6 petals, they're each 30 degrees off from each other. Okay, so they're 60 degrees off from each other. I'm taking 360 and dividing it into 6. Okay, or in this case, take 360 and divide by 4. Each petal is 90 degrees off from the previous petal. So once I get 1 petal graphed, I have all of them. That's the idea. And really, you don't even need the full petal. Think of it this way. I'm going to just destroy all my handiwork here, because it's a good question. I mean, I think it's legit for somebody to say like, hey, I really want to know, how would you graph that? Like, what if I just want to know how to graph that very quickly? So I'm graphing right now the cosine of 2 theta. Here's how I'm going to do it. I'm going to start the short little table. I'm going to start with theta equals 0. When theta is equal to 0, r is 1. So I plot that point. I plotted that point actually in red right here. Ignore that bottom half. And then because I know the angle's going very quickly here, it's twice as fast as a normal angle, I don't want to just jump to pi over 2. Excuse me. I don't want to jump to pi over 2 because that's going to complete too much of the curve for me. I want to take finer steps the faster it moves. So what I'm going to do is, since going twice as fast, I'm not going to look at pi over 2. I'm going to look at pi over 4. I'm going to look at half of the angle I would have normally looked at. So again, twice as fast implies look at 1/2 times pi over 2 next. If it was 3 times as fast, I'd look at 1/3 times pi over 2, and so on and so forth. So watch what happens when I try pi over 4 here. If you try pi over 4, cosine of twice pi over 4 is cosine of pi over 2, and that's 0. So I know that by the time I'm facing a 45-degree angle, I am dropping a rock at my feet. I'm already immediately right here. This point right here is 0, comma, pi over 4. Remember, it goes radius and then theta. So I need to decide, let me erase all this in here so that you can see that if you were legitimately just trying to figure out how this goes, you would have only these 2 points. So what you need to do now is decide, did it go this way or did it go this way? Well, now that you could either just take an educated guess and say, well, the cosine's positive between angle 0 and angle pi over 4. So I know that it's here. This is how far out I'm throwing rocks. Or you just plug in an angle between 0 and pi over 4, like pi over 8. Now you may say, but I don't know the cosine of pi over 8. And I will say, don't worry, because you're not going to actually deal with pi over 8. When you plug in pi over 8, what's twice pi over 8? Pi over 4. And that's 1 over, cosine of pi over 4 is 1 over root 2. So that tells me when I'm facing 22.5 degrees, basically right facing this direction, I'm throwing a rock in front of me. 1 over root 2 units. So I happen to know that it does actually follow a path in like this. Now, as long as, trust me, I'm getting to your question, which is, how do I know how to graph that? As long as I know that that's a 4-petal rose, and I know there's a lot of symmetry, then I know that petal has a bottom half to it. I don't care about the path it travels. I'm just going to draw it like that. And I also know that 4 petals implies each petal is 360 divided by 4, or in other words, 90 degrees from each other. And now I have the entire graph. So I would just turn 90 degrees and recopy this petal. And I would turn 90 degrees and recopy the petal. I'd turn 90 degrees and you could see that my drawings are terrible. It's just a terrible drawing. That's probably not any better. Just slightly. Okay. That is a terrible drawing, but whatever. All right. So there you go. That's how you do it. Now you can do the same thing for the sine. The sine, I'll use blue for the sine. Again, facing an angle of 0 for the sine, well, the sine of 0 is 0. So when I face an angle of 0, I'm dropping a rock at my feet. Graphing the sine now, okay? And then I will just copy the points that I used over there. So I'm going to do pi over 8 and pi over 4. I'm actually going to write down the pi over 4 first. So the pi over 4, sine of twice pi over 4 is sine of pi over 2, and sine of pi over 2 is 1. So this tells me when I'm facing an angle of pi over 2, pi over 4, I'm throwing a rock 1 unit in front of me. So somehow I got from the pole, waiting for it, there we go, all the way to pi over 4, or 1 comma pi over 4. And I want to know, how did I get there? Did I go up like this and go there? Or did I go over like this? And the answer is I actually went over like this. Because if you look at pi over 8, so I'm not quite facing pi over 4, but I may be facing this angle right here. Wait for it. There we go. That angle right there we're probably facing. When you plug in pi over 8 into sine of 2 theta, you will get sine of pi over 4, which is 1 over root 2, which tells me when I'm facing an angle of pi over 8, which is 22.5 degrees, I'm throwing a rock in front of me. So it is traveling in this direction. And due to symmetry, that pedal will come back here like this. And again, there's 4 pedals, so each pedal is 360 degrees divided by 4 or 90 degrees off from each other. So here's the next pedal, which I'm just chicken scratching out now. Here's the next pedal, and so on and so forth. Terrible drawing. I get it. It's terrible. So we want to know, I don't make fun of my drawing. We want to know what is the area that lies simultaneously in both these curves. Well, this is what I'm highlighting here, or what I'm squiggling on right here. These are all the sums of these green areas, even this one right here, which is misdrawn. This is totally misdrawn. This is totally misdrawn. But anyway, all these areas are lying simultaneously within those 2 curves. So do you think I'm going to sit here and find 1, 2, 3, 4, 5, 6, 7, 8 areas separately? No, I sure hope not. You better believe it. I sure hope not. Yeah, that would be dumb. Don't do that. So you notice, even though my drawing doesn't show it, all of those areas are the same area. So I could just find this area and multiply by 8. And I'll tell you that it even gets easier than that. Because if I look at this area, I'm going to go ahead and just make it really clean here. What was it, blue that we used for below? And red for above. Here's that area of intersection, the first area, this area right here, okay? You have to wait for it because it's very slow on my end. Yeah, that area right there, okay? So take a look. I've just redrawn that area. It's still not right. I would like that to bow out a little bit more. There we go. That's actually a lot better. Okay, so that's that area that they have in common. Now, do I actually even have to find that total area? The answer to that is no. You don't have to find that total area. You could find just half of it. And then when you double that, you get that total area. So we could actually just find maybe this little lower area right here, let's just say, and multiply that by 16. Because multiplying by 2 will give me 1 petal, and we have 8 altogether. So this point here is the pole. Let me just write that in so that you guys can see what I'm talking about. And while it's catching up to me, I'm going to say that point at the other end is the point of intersection. So I just need to know what's the first time that these 2 curves will meet. Remember, when I was drawing this out, my red curve actually started, wait for it, give myself a drink while it catches up. right there. And the particle is just kind of lazily moving along here. It's actually not lazy at all. It's going pretty quickly. And then it eventually gets to this point. It continues forward, but it eventually gets to that point. The sine, on the other hand, started at the pole and followed this path right here. I'm waiting for it. There we go. And again, that's the first time for the sine that it'll hit this cosine curve. So we just want to find when's the first time these two curves meet. And then that will give me where I have the tip of that first point of intersection. So I'm going to integrate from 0 to that, because this is the sine curve right here. That's the sine of 2 theta. I want to integrate from theta equals 0 to theta equals the point of intersection. That's how it's done. So let's go ahead and find that point of intersection. Easy breezy. So let's take a look at the two functions. We have sine of 2 theta and cosine of 2 theta. Oops, that was supposed to be a 2, but it didn't quite work out for me. I even charged this pen today. Divide both sides by cosine of 2 theta, and you'll get this. Now, generally, I tell people, don't divide both sides of an equation by a variable statement or a variable expression, because you don't know if that variable expression is 0. However, I happen to know that when these two curves meet, the cosine of 2 theta, which is how the red curve there, is not 0. Its distance away from the origin is non-zero. It's actually far away from the origin when they meet. So I happen to know that when they meet, it is okay for me to say, let's just divide both sides by cosine of 2 theta so I can solve that equation. I'm definitely not dividing by 0. And I happen to know the tangent turns into 1 at pi over 4. This implies 2 theta is equal to pi over 4. Technically, it's pi over 4 plus pi k is when the tangent turns into 1. But I don't have to worry about the pi k business because I'm finding the first time that this equation is true. Dividing both sides by 2, that's theta equals the lovely pi over 8 that we actually had by chance. That was totally by chance that we had in our table. Completely by chance. I was not a genius by making that move. I was an accidental genius. All right. So that point of intersection is at theta equals pi over 8. That's where they meet. So I've taken a huge problem, which is finding all those overlapping areas, and reduced it down to, let's just find half of a petal. We'll double that to create a whole petal and multiply that by 8 to create all those little sub intersection areas. Great. So the total area is going to be 16 of those 1/2 integral from theta equals 0 to theta equals pi over 8 of. Now, be very careful here. It's not r outer minus r inner, or r outer squared minus r inner squared. If you take a look at our highlighted area here, it is literally just saying I need find the area emanating from the pole out to this edge. And this edge, as you see in blue ink below, this edge is the sine of 2 theta. So I'm not even involving that cosine of 2 theta in this discussion from this point forward, because I only used it to find the point of intersection. Really, this area is just going to be the sine of 2 theta. So squared, though. Remember, it's 1/2 r squared theta. So it's the r squared is going to be the sine squared of 2 theta. And then d theta. again, just to remind you, 1/2 r squared theta is the area of the sector. And so when you're doing small sectors, that theta is a d theta. All right. Now we can just zoom through. That's 8 integral 0 to pi over 8, 1/2, 1 minus cosine of the double angle, d theta. You get to use that power reduction formula or half angle identity over and over again. And then this ends up being 4 times theta minus 1/4 sine of 4 theta. Do I want to say something about that? No. From 0 to pi over 8. 4 times pi over 8 minus 1/4. Sine of 4 times pi over 8 is sine of pi over 2, which is 1. Let's see, Veronica, where does the first 1/2 in front of the integral come from? It's from this right here. It's from that that formula, which is 1/2 r squared theta. So whenever you're finding the area underneath the polar curve, it's always 1/2 r squared d theta, because they're small wiggles in theta. So it's 1/2 r squared d theta really is what you're dealing with. I could put the d theta there so you can see it. And yeah, not a problem. And so that's the core formula you're using. And then obviously, if you're using symmetry, you get to double that up or triple that, or in our case, multiply it by 16. But this is pretty much done. This is going to be pi over 2 minus, let's see, 1. That's the intersection area, all of them, because I multiplied it by 16. It's a little bit, it's not actually very much. It's not a huge area. It's a very small area, maybe about a half or something like that. Yeah. Just double checking my math. Yeah, perfect. And you guys have had great questions today. So if you still have questions, I'm totally fine to take those. Or at least you had really good, the graphing one's good. They're all good. The other one I'm looking at is that I forgot the 112. That's my fault. All right. So that's kind of, in my opinion, the worst case scenario is when you have an n-pedaled rose. If we hadn't used half the pedal, would we have needed? Yeah. So the question's coming in. If you didn't use half the pedal, how would you find it, right? Well, you'd have to have two integrals. You would have the integral, the area underneath this blue curve. When I say under, I mean from the pole to the blue curve. And then you would need to compute a second area, different second area, not different, but you'd have to use different integral of the area between the pole and this red curve, which is the cosine of the double angle. So you'd have to have two integrals working. Yeah. So you can see why symmetry in these problems is going to be super powerful. Use it, please, because otherwise you're going to just do extra work you don't want to do, right? Always try to look at it geometrically and say like, well, all these areas are the same, so let me just take half of this area. Yeah, not a problem. It's a good question. So, all right. Final topic. Arc lengths, right? Everything comes back to arc lengths in this entire unit of materials. Pretty much arc length. So here's where I'm going to summarize some statements. You now have this arc length formula. Obviously, when you're computing arc length of a curve, it's that always, okay? But now the choice, you have a lot of choice. And in fact, I created a video yesterday and I uploaded it this morning. Sorry, it took me so long. I just didn't get around to it. But I created an extra video in the 10 point. Oh, I know I did upload it yesterday. It's in the 10.2 section. And it was just some extra stuff. Finding I think that one was an area problem, but it still kind of showcases this idea, which is when you start working with parametrics or arc lengths or polars, you start having a lot of options in front of you. So I'm going to say where, well, if you were handed a function and your function was a function of x, well, ds is just equal to the square root of 1 plus dy dx squared dx. That's if you were handed a function of x. In fact, let me just write that up above. If y is a function of x. Or if instead you were handed a function of y, then the arc length formula is, I just happen to have a habit of writing it dx dy here, squared plus 1. It's the same idea, but I just do it that way just because of how I do the Pythagorean theorem. But it would be that. And again, it would be that if you're handed x as a function, I'll write it as g instead, a function of y. Now, the interesting thing here, and I didn't make a big stink about it when we talked about it, when we introduced it, but what if you're handed a function or a curve that could be written as a function of x or a function of y? What if it passes both the vertical and horizontal line test? Well, then you have choice. You could totally do your problem either way here. It doesn't actually matter. You'll get the same arc length, which is pretty fascinating. Then we learned about parametrics. And we learned that that would be, the arc length would be the square root of dx dt squared plus dy dt squared and then dt. And that's if you're gifted parametric equations. If x is a function of time and y is a different function of time. But now, what would happen if we were given a function? I'm going to say r is r of, but that's kind of what I'm going to say here. R of theta. What if we were handed a polar curve? R is some function of theta. Well, in that case, in that final case, it's the weirdest looking one. The arc length is the square root of r squared, which doesn't follow any of the patterns, plus dr d theta squared d theta. I'm going to write that down. This one I actually have to, I had this conversation with a student yesterday about they have a really bad memory, and they were like, I like the fact that you derive a lot of stuff because I have a hard time remembering things. And so seeing how it's derived allows me to derive it when I forget it. This is probably the one thing that I have to constantly try to embed in my brain, because deriving it is not the most entertaining action. But I will derive it here just so you see why that is the formula. But you might want to just commit it to memory, because deriving it is a little bit of just, it's not a horrible process. It's just not a fun process. So proof, let R be, well, a function of theta, where x of theta is r of theta cosine of theta, and y of theta is r of theta sine of theta, because that's really how polar coordinates are defined. So if I know that I'm working in polars, I know the x and y coordinates in the Cartesian coordinate system are just going to be r cos and r sine, respectively. We know from parametrics that ds is equal to the square root of dx d theta squared plus dy d theta squared d theta. it turns out that, honestly, polars are just parametric curves. That's really what they are. That's why we treat them together simultaneously. They're just parametrics. If you think about it, x is a function of theta. Y is a function of theta. So they're really just parametric curves. But we call them polars because they're very specialized parametric curves. Okay. So in this case, we're going to go ahead and find out what is the derivative of x with respect to theta? What's the derivative of y with respect to theta? And we happen to know, I'm just going to make a very long bracket here. Since x is r of theta cos of theta, it'll be dr d theta, that's the derivative of the first, times the second, plus the first times the derivative of the second. Well, the derivative of cosine is a negative sine. That's the derivative of x with respect to theta. And now we're going to square that in a little bit. Plus, you can see how long I've written this radical sign, that you don't want to derive this. You just want to memorize this. It's one of those sad statements. But for y is r times sine. So derivative of r is dr d theta times the sine plus r times the derivative of the sine. And again, squared that. And we know there's a d theta hanging off back. Take a drink. All right. Let's go ahead and square everything out. Equals square root of, it should even be longer than this because, right, you gain more terms when you square. So you'll have that dr d theta being squared. I'm just going to write it that way. Dr d theta squared times the cosine squared. Let's see, minus 2r dr d theta cosine theta sine of theta. That's just me, like if you have a minus b quantity squared, it is a squared minus 2ab plus b squared. So there's my minus 2 in the product of these two things. That's how I got that. If you're wondering, like, how did he get that magical whatever? That's how I got it. And then plus r squared sine squared. That is the expansion of just the first squared term. In blue, I'll do the expansion of the second squared term. Here we go. Plus dr d theta squared sine squared of theta. This one, because it's positive, is going to be a positive 2 times the product of those two. So I'm going to write this r dr d theta. What do you have? Sine and a cos? Or is cos and a sine just to match it up? And then plus r squared cos squared. Barely fit that in there. A lot of, just a really terrible thing. But what's nice is this picture right here cancels with this big old picture right there. And all of a sudden, this compresses down significantly. Not only that, but you could see, I'm just going to go ahead and move this out of the way. You can see that our dr d theta squareds are attached to a sine squared plus cosine squared. I'm going to actually take my time with that and just say dr d theta squared times cosine squared theta plus sine squared theta, which we know is 1. Good old trig. And then we have an r squared, but that r squared is also attached to a cosine squared plus sine squared. Sort of off my screen that sine or the cosine squared is, but there we go. And so we just have to check. So we get down to the square root of dr d theta squared plus r squared d theta QED. That's it. Now, I am assuming nobody wants to have to reprove that every single time that you run into that formula. So yes, that's the one. Commit that to memory, just because otherwise you're going to have to reprove that every time. You can see there's just tons of places where things can go wrong. So there is our formula. Yay, done. So now we're going to use it. Find the length of r equals theta from 0 to 2 pi. Very friendly example. Mainly because these, just to let you know, for normal polar curves, arc lengths are a little bit gnarly. They have to be very specialized examples to work well. So arc lengths and polars are not always the best. If you think about it, the reason why is because you, first of all, polars are sines and cosines normally. Here's a case where it's not, but normally they are. And if you think about having the square root of sines and cosines, hopping back here, the square roots of sines and cosines are a bit of a mess. And so that's why arc lengths and polars can be a little bit messy. So just be prepared that can happen. Generally, if that does happen, we use Simpson's rule or something like that to just speed up or to get to an approximated answer. So find the arc length of r is equal to theta. I'm just going to graph this out. This is one of those that you should naturally just kind of be able to figure out. If you're facing the angle of 0, let me put angle versus theta here, or theta versus r. If you're facing the angle of 0, your radius is 0. If you're facing the angle of pi over 2, your radius is pi over 2, and so on and so forth. So basically what that means is as you turn, the angle with which you turn through should match the distance you're throwing rocks. Something like that. Okay. So it will look, again, like that conch shell that we had for the square root of theta. And I want to find the arc length of that from 0 to 2 pi. Arc length is always integral ds. Just look at the problem you've been handed and decide which version of ds you want. From this point forward, think of it that way. Like, all right, I need to use arc length here. What kind of function am I handed? Oh, polar. Well, then my hand is forced. I immediately know ds is going to be that one I have to memorize, square root of r squared plus dr d theta squared d theta. So that's what I'm going to trade it out for. Square root of r squared plus r prime squared. You could write it that way, d theta, where theta is going from 0 to 2 pi. I cannot use symmetry here because if you look at the picture, there's just none. There's no symmetry. I have to have another step here. So let's sub in the information we need. R is theta, so that's going to be theta squared. R prime, well, R prime is 1, right? Dr d theta is just 1. So 1 squared is that. You get this. Yeah. So how would you like to integrate this? Yeah, I agree. So Avi and Samuel said the same thing. Like, probably trig sub. Yeah, I'd probably do that. Be very careful when you do a trig sub here, because all of our previous trig subs would involve letting x equal something like a sine of theta or tan of theta. Theta is taken. So because theta is taken, you can't let theta equal something with theta. So just be very careful with that. We're going to let theta equal, let's see, that's going to be like a tangent. So tangent of, let's just use alpha. We'll keep Greek here. Which implies d theta is equal to secant squared of alpha d alpha. Also, somebody had mentioned yesterday day before yesterday in one of my office hours about watching a video in one of the examples. And they said, oh, and then they opened up a table that had all these integrals. That could have been in class too. I can't remember, but you will see people that say, oh, well, let me look at a table to find out what this turns into. I don't want you to have to do that. I want you to be able to do this by hand without looking at a table. It's a good exercise. It's the difference between watching somebody work out and working out. You gain nothing from watching somebody work out. You gain nothing by going to the table. You don't learn anything. So just try to exercise the brain there. All right. So we're going to make that substitution. Theta, by the way, being 0. So this is one of those substitutions that is incredibly weird. If you allow theta to be 0, tangent of alpha equals 0 means that alpha would be 0. If you allow theta to be 2 pi, tangent of alpha, if you allow theta to be 2 pi, tangent of alpha equaling 2 pi means that alpha has to be 0. You can be easily fooled that this goes from 0 to 0. It doesn't. But because of that weirdness, I am going to remove the limits of integration. This is a really weird case. I'm going to say that again. I'll put this in red because this is kind of a big warning. It's a weirdness for a couple reasons. Let theta equal 0 will imply that 0 is equal to tan of alpha, which implies alpha has to be 0. Everybody nods their head and they say yes. Letting theta equal 2 pi, well, that will imply that 2 pi, oh, never mind. I misspoke. 2 pi is equal to tangent of alpha. I was thinking that was going to be 0, but never mind. I misspoke. So please forgive me. Theta equals 2 pi. You could actually do this. I still probably wouldn't do it this way, but this would imply that alpha would be tan inverse of 2 pi. I probably still would not do it that way, to be honest with you. So for right now, I guess there wasn't a warning there. I'll put a note instead. For some reason, I was just thinking it was going to be 0, but that's not true. So I'll put a little note instead. Sorry about that. We still are going to have an issue, sort of. So let's go ahead and say this turns into the integral. This is, again, one of those rare cases where I'm not going to change the limits. Instead, I'm going to integrate this without changing the limits, and then I'm going to move everything back into the world of thetas in the end. It's just a little bit better to do that in this case because my limits go from 0 to tan inverse of 2 pi. Anybody know that offhand? I didn't think so, so let's not bother with that. So if I do this, d theta gets traded out for a secant squared of alpha, d alpha. And we happen to know that subbing in tangent of alpha, there we get tangent alpha squared plus 1, which is secant squared. Square root of that is going to be the secant. So we actually get a secant cubed. And we happen to know the antiderivative of the secant cubed is 1/2 the derivative of the secant plus 1/2 the integral of the secant. That's done by parts if you're really concerned about that. And what I'm going to do is just draw a picture for this tangent of alpha here. I'll use a green triangle for that. The angle within the tangent is actually alpha, and its output is theta over 1. All right. And now I'm just going to steal everything from that picture. Okay. So this will be equal to 1/2. Secant of alpha is the square root, theta squared plus 1. Tangent is going to be just the theta. Actually, I should have left myself some room. So I'll just Let's move this over slightly. There we go. Plus 1/2 the natural log. Yeah, I'll go. You don't have to say absolute value here because it is actually going to be non-negative. But secant is the square root. Theta squared plus 1. Tangent is theta. And we're going to evaluate this from theta equals 0 to theta equals 2 pi. There we go. So that'll be when you plug in 2 pi, you'll get 2 pi times 1/2 or pi root 4 pi squared plus 1 plus 1/2 natural log of root 4 pi squared plus 1 plus 2 pi. And then subtract off when you evaluated 0. However, when you evaluated 0 here, this is 0. I say this, I wait for it to zoom in. There we go. And we have the natural log, wait for it, of 0 plus 1 plus 0, or in other words, natural log of 1, which is 0. So there's our answer. That is the length of the curve. Yay! I technically have one last example. You can hear me sigh over this last example. Sigh. This is actually, you know what? This is probably good for us to do because this is like a good exam question. I like to ask set up, but do not evaluate, especially in chapters 8 and 10, because you get a lot of integrals that you just can't evaluate. And so it's nice to say, set this up, don't evaluate. So you know exactly what I expect on an exam sometimes. Also, really good example, because again, we're going to graph a multi-pedaled rose. Remember, if your polar equation is r is equal to cosine or sine of a multiple angle, it's a multiple petal rose. If it's an odd number, an odd argument on that theta, it'll be that number of petals. So it's 3 petals. So let's go ahead. What is going on? Sorry, my laptop tends to not charge now. It's charging now. That's good. I think it's just because it's fully charged. Maybe that's why. That's probably why. We'll just pretend as though that's why. All right. So let's go ahead and do what I think you should do, because Raj had asked this earlier, and I thought it was such a good question. How would you graph something like that? I'll start by just saying, well, let's build a small table. Nothing massive, just something real quick. So theta versus angle r. Let's find out what initially happens when we're facing an angle of 0. Well, cosine of 0 is 1. So I'm going to go ahead and just plot that out. It's the pole and the polar axis, and I'll use blue for my curve. So let's just say this is 1 unit out. So that's a radius of 1, angle of 0. All right. Now I'm going to start turning. And when I turn, I'm going to turn intelligently. Normally, I would go to pi over 2 next, but I'm going to go to 1/3. It's basically the reciprocal of that coefficient, 1/3 of pi over 2. I'll even write that in here, 1/3 of erg pen of pi over 2. And that will be pi over 6, which is the cosine of pi over 2, which is 0. So this tells me by the time I'm facing 30 degrees, which is pi over 6, that angle right there, I've dropped a rock at my feet. Now I'm going to go ahead and ask. So that point right there, by the way, I'm just going to zoom into it. That's distance of 0 when I'm facing an angle of pi over 6. So between angle 0 and angle pi over 6, I need to know, did it go this way or did it go this way? Well, I think you should be able to figure it out. The cosine is positive initially. So it's going to be in front of us this way. We're turning this angle anyway, so it's definitely going to be a decrease in distance. So we have this path of travel right here. Now, that being said, I know that these end petal roses are symmetric. So this is part of a leaf. Let's go ahead and draw the other part of the very same leaf. I don't even need to know any type of angles or weirdnesses there. And then I'm going to go ahead and figure out what degree are these leaves off by. So each leaf, each petal, I should say, is off by 360 over 3, which is 120 degrees. So all I need to do is rotate this petal 120 degrees to find the next petal. So probably the easiest way to do that is to draw it, because this angle right here is angle 0. So I'm going to draw in just lightly here, angle 120 degrees. I should have actually drawn it. Give me a moment. There we go. I'm going to draw in an angle of 120 degrees just so I have something to work with. That's my angle of 120 degrees. And what I'm going to do is draw in here a little petal. Is that the same distance? I don't think it is. That's about the same distance. All right. And then the next petal will be 120 degrees off of that. So in other words, at 240 degrees from the origin. So there we go, something like there. And I'll just draw its terminating point. You know, I've drawn worse. You've actually seen it. So there we go. So that's terrible. What am I going to do? You know what? It's just terrible. All right. So set up an integral for the length of the 3-leaved rows using a strategy of, you know what? Let's cross this out. Because I would never tell you that. I would just say, find the length of the 3-leaved rows. That's all I would say. Find the length of this 3-leaved rows. What's nice about it is actually you didn't even need the full curve there. You could have just said, okay, well, I'm going to find this length right here. And then if you think about that picture, aren't there 6 of those lengths in total? Yeah. So multiply that by 6. Multiply by 6. So let's go ahead and do that. The length, the full length is going to be 6 of those lengths. And that first length went from an angle of 0. My handwriting is usually really nice on a board, but it's terrible here. Starts at an angle of 0, and we already wrote it in here. It terminates at an angle of pi over 6. So I'm going to go ahead and integrate from 0 to pi over 6. We're multiplying that by 6 in the end to get all the lengths. And remember, this is a square root of r squared plus r prime squared d theta. That's actually kind of the easiest way to remember this formula. It's just r squared plus r prime squared. R squared being cosine squared of 3 theta. And then r prime, well, r prime, I'm going to draw it off to the side here. If r is cos of 3 theta, r prime is a negative 3 sine of 3 theta. Squaring that, you get 9 sine squared of 3 theta, that is. And that's where we stop, because that is not integrable. It can be. I mean, that's 1 plus 8 sine squared, but still, it's pretty gnarly to do. So it even says in there, like, why is this integral difficult to compute? It's because it's a square root of a trig function. Essentially, you can sort of modify it slightly. A lot of people will look at this and think, okay, I can steal one of the sine squareds, so I have a cosine squared of 3 theta plus a sine squared of 3 theta, and that would be this. And you're absolutely right, it would be, actually. Hold on. But now what are you going to do? And if you say trig sub, good luck. This is not going to work out well for you. So it turns out that this is one of those integrals that you have to do a numerical approximation for, which we won't have to do because we're not going to. We're done. All right. So let me summarize really very quickly. By the way, notice we didn't do surface areas. We don't do surface areas with polars. That's a no-no. I don't want to do surface areas with polars just because it's not fun. So what is this unit of material all about? Well, it's about areas. You know, area is just the integral. X equals, I'll actually say x low to x high, some low x value to some high x value of y dx, or an integral from y low to y high of x dy. That's from your Calc 1. Okay. But in parametrics, the area is equal to the time value associated with x low to time value associated with x high. It has to still go in the same direction, okay, of y. And remember, I'm just going to say this: x is a function of t, and y is a different function of t. That's g. That's supposed to be a g. So y would be g of t. Dx would be f prime of t dt. That's all you have to do. You're just taking the derivative. Dx is f prime of t dt. If you're doing it in the vertical direction, again, it goes from some time value. Let's go from lambda to, if I put pi there, you guys are going to hate me. So let's go to delta. Except you have to actually draw a delta in here. Okay. And it is the integral of the x value, which is f of t, dy, but dy is just g prime of t dt. Again, the time here is linked to y low, and the time at the upper limit is linked to time to y high. Just like the time in the upper limit for the first one is linked to x high, and the time for the lower limit is linked to x low. That's the area in parametrics. In polars, the area is just 1/2. Actually, I'm going to put the 1/2 inside just so it keeps the formula stuck together. The integral from theta equals alpha to beta, let's just say, of 1/2 r squared d theta. If you have an outer minus an inner, you subtract like you did before, right? R outer squared minus r inner squared. Those were the only area formulas we had in this entire unit that I can think of. And then the most important idea, in my opinion, is arc length. And we wrote down all those on the previous page, but I'll just quickly, ds is equal to square root of 1 plus y prime squared dx, or root x prime squared plus 1 dy, or square root of, I have to zoom in because otherwise it'll get really messy, dx dt squared plus dy dt squared dt, or square root of r squared plus r prime squared d theta. That's it. I mean, that's the only thing with arc length, right? So the length of an arc is just integral ds, where ds is one of those. Again, something that I just didn't really focus on, I might make a video on it today just to do it, just to give you one last oomph there, is that if your function that you're handed is a function of both x and y, then you have the ability to do whichever one you want to do. You could do this first or this second version right here, your choice, whichever one just makes better sense to you. And that's one of the, actually, I don't need to do that because I could do that. I made a video, kind of had that idea in it. Then finally, the only other thing other than centers of mass, I get that was also in this, but that's just memorizing formulas. Honestly, nothing more than that. The other thing was surface area, right? Oh, and derivatives. We did do derivatives. I should probably mention that too. But surface areas. Okay. Well, surface area is always 2 pi radius. When you're talking polars, writing r there is a little bit dangerous for some people. So 2 pi radius of rotation ds, right? The radius that I mentioned there is the distance from axis of rotation to the curve. ds is any of those 4 above that you want to use, as long as you're keeping it consistent. In other words, don't compute ds in terms of polars and then do everything in terms of a function of x. That would be broken. You couldn't do that. But otherwise, that is I mean, there's nothing else I can say about that, because once you make your choice for with respect to x or y, it sets everything else perfectly. And so the only other thing we had was derivatives, right? Derivatives. If you have, actually, it's the same in both cases. So dx, sorry, x is a function of t, y is a function of t. That is, you're in parametrics. Then dy dx is dy dt over dx dt. Yay. And something that does creep up every once in a while is the second derivative of y with respect to x. That's the derivative with respect to time of dy dx divided by dx dt. And finally, polars. Dy dx. This one, you know, it's funny because this one I don't memorize. I just rederive every single time. Let me zoom in because my pen is just being a pain today. Dy dx. All right. I actually, with polars, I never memorize it. I just rederive it. Dy dx is, again, it's dy dt over dx dt, but with polars, it's dy d theta over dx d theta. If y is equal to r sine of theta, which it is, and x is equal to r cos of theta, which it is, then dy dt, or dy d theta, sorry, is dr d theta times sine. I do have to zoom out slightly, otherwise my pen gets really choppy. Plus r times the derivative of the sine, which is cosine. And then the denominator, derivative of x with respect to theta is dr d theta times that cosine. And then minus r times the sine, because the derivative of the cosine is a negative sine. And that is basically everything that you could expect from this entire chapter, with the exception of little things like find the formula for the the tangent line to the curve at whatever. And then obviously there'll be a problem on a single problem on moments and centers of mass, right? Finding the center of mass on this plate or something like that. Done. You're done with Calc 2. Well, okay, you're not done. You have 2 exams left, but you have an exam next Wednesday, and then a week later you have your final exam. But what's beautiful about this is as you study for your exam next week, you're going to use integration techniques, which is what your second exam was. So you're studying kind of for your final as you're studying for this, and you just finished sequences and series, so you're pretty fresh with that. You'll have to kind of review a little bit of that. On Monday, I'll tell you what's not on the final, so it targets your studying a little bit better. All right. Now, I will be back here in 8 minutes. If you're not going to be there, that's fine. Have a wonderful weekend. You are welcome to show up or not on Monday. It's not a requirement, but I'm going to be there and just to talk about kind of what we're going over. And I'll post the videos for today. And I already posted 10.3 video this morning from Wednesday. I'll post 10.4 videos today. Okay. All right, you guys have a wonderful, wonderful, wonderful weekend. Study hard for all of your exams. If nobody said it, they should. You guys are awesome students. You guys have done a great job. I'm very proud of what I'm seeing from my students. So you guys are doing an incredible job in a tough environment. So yeah, and the question's being asked, even though there are no more lectures, do you have office hours? Yeah, my office hours are standard next week, except for starting Thursday when finals week starts. I will send out a message, or I'll put it on our site, what my finals week office hours are going to be. That way they have to adjust because times don't work out well. So I will send that out. But Monday, Wednesday, Tuesday, and Wednesday, my office hours are the same. All right. And let's see, would it be possible to make all the exam study guide? Yes, actually, Christy, what I'm going to do is I'm building a final exam study guide. So that would be better for you, because then you can see exactly where I'm targeting for the final exam. I think that would be much better for you. Yeah, so don't worry about me opening up other study guides for the final exam. It'll be a single final exam study guide. Okay? All right, you guys, I'll be back in, like I said, about 6 minutes. Take care.